All right, so for derivatives within economics, we're going to look at the marginal cost. So the marginal cost of production is the rate of change of cost with respect to the level of production. Now the variables we're going to use here is a cost function is going to be the cost for each unit produced. So that's cost, and X is unit produced. And for some variables, I think, for example, I think the cost in dollars and the tons of steel that go into the unit is the example um, the book uses. So the marginal cost the change in cost per unit is going to be the limit as h goes to 0 of c of x plus h minus c of x. But what we're going to do is do it over 1, the cost of one additional unit. Oh, no, let me make this clear. The marginal cost is the derivative. If we do it and we look specifically at one additional unit, then we can look at this relationship. And we can approximate this near an area. So the total cost function, as your book is going to say, is represented by a cubic polynomial. So we're going to have different coefficients. And delta is the fixed cost. So, right, if you have a factory that is producing units of things, the factory has base costs. The other terms are variable costs, like the raw materials, the power usage, the man hours that need to go up and down. Fixed costs could be the rent and your base salary that you need to keep the factory open. And you could have an increase in man hours over time that goes, or the man hours that are added on top of for each unit produced. So your book, usually a cubic polynomial is adequate to capture all the behavior. If you linear algebra, we'll look at some of the different coefficients that could come about. This economics and economists and more complex cost functions and production chains, these can be more complex polynomials, but a cubic polynomial usually captures most behavior of your cost functions. So the book's going to give us an example, and they're going to say, suppose the cost to produce X radiators, so C of X is going to equal X cubed minus 6X squared plus 15X. Notice there's no delta when 8 to 30 radiators are produced. And the revenue, how much money you make, is related. And this is the dollar revenue for selling X radiators. So the cost of producing one more radiator per day. I do want to see, sorry. This is X is radiators per day coming out of the factory. And so the cost of producing one more per day, we'll take the derivative of c of x. So 3x squared, right? We bring this down front, bring the power down, multiply this out front, bring the power down, and this drops it down to a constant. And so the cost of producing one more per day, 110 are produced. Oh, we'll drop in 10 here. Or what is it, 195? So the cost is 195. And so the marginal, the additional cost is about $195 per to add one more radiator to production. And then in the revenue is affected, right? So we're going to go from 10 radiators a day to 11 radiators per day. Then in the revenue will be affected similarly. So we'll take the derivative of here, we'll bring the 3 out front, bring the power down by 1, bring the 2 out front, bring the power down by 1, and we get plus 12. So the revenue, when we're at 10 radiators per day, and we're going to increase towards 11, we're moving forward 1. $252. So to increase by one radiator per day, you're going to see a net a profit of $57 associated with those costs on it. And notice what we're doing is we're getting the derivative defined within certain applications. All right, the last one I'm going to look at is sensitivity of change in genetic information. This is a biological use of a derivative. Again, I think I'll separate these on different videos.